Now, there are two questions that we would ask that now that we know that this is a first order reaction. We would ask actually three types of questions. One, what is the value of K and units? And there's a couple of ways that we could do this. One, let's take our equation and we'll pick a time and a concentration at that time, and we'll solve for K. So let's just use this next one. And at time 50, the concentration is 0.0707. So let's say I wanted to solve for K. I'm going to take the natural log of 0.0707. Of course, that's the concentration in moles per liter. We're trying to solve for K. We picked a time of 50 seconds plus the natural log of the concentration at time 0. And now we're going to turn our calculator back into just a regular old calculator, and I want to get K by itself. So to do that, I'm going to subtract both sides. I'm going to subtract the natural log of 0.1, and then I'm going to divide by 50 seconds. So here's how this is going to look. We're going to take the natural log of 0.0707 moles per liter. We'll subtract from this the natural log of the concentration at time 0, which is 0.1, and we'll divide by 50 seconds. Now, when we take the natural log, the units are going to disappear. So our units for K will be seconds to the -1. So we're going to turn our calculator back into a calculator again. And we're going to, let me move this over so I can see what I'm doing. We're going to take the natural log of 0.0707. From that, we will subtract the natural log of 0.1. And we'll divide, well, let's take care of this first. And we'll divide this answer by 50. And here is our rate constant. It is 0.00693, and it is a negative number, as it should be. And you could write that as 0.00693, or 6.93 times 10 to the -3 seconds to the -1. Now that's one way that we could do it. Or, if you want to be fancy, you already had this graph. And you got that graph from these statistics. So you already have this graph, right? So what we're going to do is we're going to go back to Stats, and we're going to click over to Calculate. And notice that number 4 says linear regression, and that this AX plus B sure looks a lot like MX plus B. So if that's the case, then clicking number 4 should give us a linear regression where the slope is our value for K. And then you don't have to solve using the equation. So let's see what happens. Let's make sure that we are telling this calculation to run the linear regression of the graph that we're already doing. And so we want our x-axis to be L1, but we want our y-axis to be L3. So get on down here to calculate. And there it is, ladies and gentlemen. The exact same answer, 0.00693. So there's a couple ways that you could calculate K. Now, how are we going to use this? 2, what is the half-life of this reaction? Half-life is a term meaning how long does it take for the reaction to run to the point where our concentration is exactly half of its original. And let's remember that our original concentration was 0.1. So right here is half, and it says it takes 100 seconds. It's not always the case that it will be that cut and dry, so you'll need to calculate half-life. But for this one, it's nice because we know what answer to expect, 100. So the equation for a first-order reaction to find half-life is 0.693 over K. Notice that our value for K, when we answered this, is negative, and that this is negative K. So we don't need these negative values here, right? They were already taken care of in the equation. So if we want to find half-life, 0.693 over K, which we've already found, 6.93 times 10 to the negative third, seconds to the negative 1. And since seconds to the negative 1 is in our denominator, that means our answer for half-life will be in seconds. So we'll take this and we'll say 0.693, divided by our value for K, which we already got. We'll say 6.93 times 10 to the negative times 10 to the negative third, 100, which is exactly what we expected based on this data. Now, the last thing you can do is find the concentration at any given time, even if our data doesn't go that far. So what we'll do is we'll pick a time and we're going to say, here's a theoretical question. What would be the concentration? What would the concentration of N2O5 be at 500 seconds? Well, you know the rate law. You know the natural log of the concentration of N2O5 is equal to negative KT plus the natural log of the concentration at time 0. So all we have to do is plug in these values, our rate constant and its units, the time, and the natural log of our concentration at time 0. So we know our K, 6.93 times 10 to the negative third, seconds to the negative 1. Notice that I'm putting the negative sign in there. The K itself isn't negative in the equation. The negative sign is already there. Times the time, 500 seconds, plus the natural log at time 0, which is 0.1 moles per liter. And you don't really need the units because when you take the natural log, the units disappear. So let's see what we get. We're going to bust out our calculator. Boy, it's a good thing we have these, huh? We're going to say, don't forget that this K is negative. Don't forget that. Negative 6.93 times 10 to the negative third times 500. We'll add to this the natural log of 0.1. And this is what we have. We'll call that negative 5.77. So the natural log of N2O5 at 500 seconds is negative 5.77. So what is the concentration of N2O5? Sorry, I'm trying to write, ladies and gentlemen. It's fighting me. N2O5 at 500 seconds. All we have to do is bust out our calculator, and we're going to use this function for the reverse of natural log. It's right here. It's e to the x. And we're going to say second e to the x of our answer. And here is the concentration at 500 seconds, 0.00313. Does this answer, 0.00313, and we'll put our units back in, does this make sense that it would be 0.00313 moles per liter at 500 seconds? Well, at 50 seconds, 0.0707. At 100 seconds, 0.05. At 200 seconds, 0.025, 0.0125. Here at 400 seconds, 0.00625. So 0.00313 lines up perfectly. That is integrated rate law, ladies and gentlemen. I'm going to stop this here, and in the next segment, I will show you how we do zero order and second order.